So, at the end of this exercise, let us go to the laboratory to where we have a demonstration experiments illustrating some of the concepts on Fourier series that we have been discussing so far. What we have here is an experimental setup to demonstrate the harmonic analysis of a square wave. We have a function generator here which generates a square wave, and that is now displayed on the oscilloscope. This is a square wave of 2 units peak to peak value or 1 unit peak value. Now what we are going to do is put the square wave through a low pass filter, which is this, so that we can allow only harmonics up to a certain order to go through and come out as the output. And the value of the output voltage will also be displayed on the oscilloscope in the bottom trace. So let us see. What we have here is a 500 Hertz square wave, and now I am putting a low pass filter cutoff frequency so that only the fundamental is passed through. And when you do that, you observe that the output of the low pass filter corresponds only the fundamental frequency, a pure sine wave, and this has an amplitude which is about 4 upon pi times the amplitude of the square wave, as we should expect. Now this is that means only the fundamental is passed through. Now if I allow other frequencies, for example, if I increase the cutoff frequency of the low pass filter so that I allow up to the third harmonic, now you can see the third harmonic frequency is also allowed. Therefore, not only the fundamental but the third harmonic is also coming through. And we can increase the cutoff frequency and allow more and more harmonics to come through, and as you can see, as you pick up more and more harmonics, the output becomes closer to the square wave. In fact, if you go to a very high cutoff frequency, it's almost a square wave. A point which you should notice here is that just at the point of jump, just immediately after the jump, there is an overshoot, as we expected from the discussion in the earlier lecture classes. This is due to Gibbs phenomenon, and immediately after any discontinuity, the Fourier series will not converge at the point of discontinuity. It will not converge uniformly. Therefore, we expect an overshoot. The surprising thing is that in the strict mathematical analysis, you should have an overshoot both immediately after the jump and immediately before the jump. So strictly speaking, mathematically you should have an overshoot here also. But in practice, experimentally you will never get that. The reason is that our low pass filters are not ideal low pass filters, in that all the frequency component that they allow will not be faithfully be passed to the output, but there will be some phase distortion, there will be phase delay. Because of this reason, you will not get this kind of overshoot just before the jump. This is also in accordance with what is called the principle of causality, because no physical device can anticipate a jump that is going to take place later. So no physical device can respond to a jump that is going to occur later and then start ringing here. Therefore, it is physically not possible for us to construct any experimental setup where you can demonstrate this kind of ringing even before the discontinuity. So this is just a demonstration of how the various harmonics go together to build up a square wave. Let us go back once again. This is when all harmonics up to, let us say, 33rd harmonic are passed through. And you go back, as you allow smaller and only up to smaller order harmonics, the waveform is no longer a square wave, and in fact, when you have the cutoff frequency just above the fundamental, only the fundamental is passed through. As mentioned in the lecture, we can perform harmonic analysis using instruments known as harmonic analyzers or spectrum analyzers. It is also possible nowadays to use the computer to effect the harmonic analysis of any given periodic waveform through software, and here is a demonstration of one such situation. We have a square wave here, and the computer has calculated the various harmonics and displayed them in the windows that are shown here. This is the fundamental, this is the third harmonic, this is the fifth harmonic, and the sum of the fundamental, third and fifth harmonics is displayed here. And we also observe this is the spectrum of this, and the spectrum shows peaks at the fundamental, third, fifth, and so on. And we also observe that the peaks progressively go down. We would expect that the amplitudes of the various harmonic orders will go in the manner 1 over n, where n is the order of the harmonic. Now, strictly ideally speaking, the spectrum should be a line spectrum. There should be just lines at the discrete frequencies. But because of the various round-off computational errors and imperfections in the system, you will only get the peaks. It will not be a pure line spectrum in the sense that you will have a complete blank between two lines. Rather, you have some kind of continuous spectrum, but with pronounced peaks at the frequencies which are present in this composite wave. The computer programs will also calculate the various amplitudes of the various harmonic components and displays them with the suitable scale factors on the screen. So this is a very convenient way of analyzing any given periodic waveform and finding out the various harmonic components. Now let us use the computer program to find out the harmonics of another waveform rather than the square wave. As a second example, let us take a pure sine wave and perform its harmonic analysis. So obviously, the spectrum consists of only one line at one frequency, which is the frequency of the sinusoid. Therefore, this is the spectrum of the sine wave. You have one spike at the fundamental frequency and no other harmonics are present. Now, if I multiply a sine wave by itself, get sine squared theta, this can be expressed as the sum of a DC component plus a second harmonic component, and that is what is shown here. This is a function which is obtained by squaring this, and the spectrum of that obviously consists of a DC term plus a sinusoid which has got twice the frequency of the fundamental, and that is, these are the two lines corresponding to that. This is a DC component and this is the sinusoid, and all other harmonics are absent. You observe that both these waveforms are very smooth in the sense that they are infinitely differentiable. So all the derivatives up to whatever order you take are continuous, and therefore the spectrum comes down, the amplitude of the spectrum comes down very fast, larger than n to the power of k, where k is any large integer that you as you wish, and therefore you observe that the spectrum dies down to 0 after a few harmonics, because the two functions are very smooth functions. What you are hearing now is the sound of the time signal which you get before the beginning of the news broadcast on the All India Radio. This is the type of wave, the type of waveform which has been given to you as a part of the problem in the last exercise. This is a 1000 cycles sinusoid which is blanked off for 9/10 of a period and then is kept on. The on to off ratio is 1 to 9. So every 100 milliseconds it is on, 900 milliseconds it is off. So this such a time signal produces this kind of sound. Now let us see the waveform of this on the screen. The sound you have just now heard corresponds to a waveform like this, where you have a 1000 hertz sinusoid which is kept on for a certain small amount of time, 1/10 of the period, and then it's switched off for the remaining 9/10 of the period. So you have a burst of sine wave and it repeats itself periodically. So this is the waveform that you get, and if you freeze this, this is how it looks. You have actually it can be produced by multiplying a sine wave with a periodic pulse train of width corresponding to this interval of time. And in the exercise, last exercise, you are given this kind of waveform and you are asked to find out the various harmonic components given the data pertaining to the frequency when it is on, and also the blank period and the mark period of the pulse train. A few comments on the demonstration you have just now witnessed. In the first part of the experiment, you had a function generator which produces a square wave. This is put through a low pass filter which allows frequencies up to a certain order to pass through, and both the square wave and the output of the low pass filter are displayed on the oscilloscope. Oscilloscope has two channels. One channel you have the square wave, and the channel below we display this type of waveform. When frequency is only up to a point which just above the fundamental frequency of the function generator is put, ideally if this is the square wave, you should get a sine wave which is the fundamental, which is 4 by pi times of the amplitude of the square wave. Some of you might have observed that the square wave, if this is the square wave, the sine wave was not sitting at this point but slightly shifted like this, as shown by the dotted lines here. This is because the low pass filter gives a phase shift when it is allowing the signals to go through, and because of the phase shift produced by the low pass filter, particularly frequencies which are very close to the cutoff frequency, you would have observed this phase shift. Those of you who might have noticed it will know that the reason is the phase shift produced by the low pass filter. It is because of the phase shifts produced by the low pass filter for different frequencies that one half of the Gibbs phenomena is lost. When finally we allowed a whole lot of frequencies, you find the Gibbs phenomena, the overshoot occurs at this point, not at this point. That is again because of the phase shifts produced by a practical low pass filter. This is the reason for this. Now let us move on to the second part of the experiment, where on the computer screen you have seen the spectra that are displayed for different types of waveforms. The spectra that are displayed there are one-sided spectra, not the two-sided spectra, not Cn versus omega for both positive and negative values of omega, but only for positive omega we are talking about the amplitude of the sinusoid versus omega. So that is why the DC is at one end of the displayed wave spectrum. So it starts from DC and goes up to higher frequencies. So you recall that this is one-sided spectrum, whatever is displayed, not the two-sided spectra that we have been talking about in the lectures. Let us go to the third part of the demonstration, where we had a time signal, that is we heard the time signal and then we displayed the burst of sine waves on the screen. Now we played a little trick there. Actually sound was of course 1000 cycle signal which is repeated 1 second, but then if a repetition rate of 1 second is too slow to enable us to capture the picture on the CRO because the writing speed is too slow. Therefore what we did was the repetition rate was speeded up. It is not 1 second but it is something much less. So that is the reason why in the burst of each sine wave you will not see 100 cycles but maybe 4 or 5 cycles only you have seen. That is because while the general shape of the waveform is the same, but the repetition rate has been increased, and that is why you would not see in the single burst of the sine wave a number of cycles. Actually the sound we have heard of course corresponds to 1000 hertz repeated at once per second. So that is the reason for this. So with these comments you can now go back and look at the demonstration once again. Please go ahead.